Good afternoon, good morning, and good evening, everyone, depending where you are. Thank you very much for joining on today's RSS webinar. So some of you may know that the RSS webinars revisit past RSS journal papers, such as A, B, and C. And these papers, we choose these papers which they already proved to be of high impact. And we hope through these revisits, we can have a better understanding of the results in these past papers. But most importantly, we really wish to create a platform for everyone to share the thoughts and to have a more high-level discussion on the general field. Well, so today's theme is on multiple testing, and we will feature two past papers. The first one is on alpha investing and will be presented by Aharoni Rosset from Tel Aviv University. And the second paper is on the ADAPT method, and this will be presented by Lei from Stanford University. Lihua's co-author on this paper, Lei Fithian from Berkeley, is also with us today. And it's a tradition for these RSS webinars. We also have a discussant, and our discussant today is Aaditya Ramdas from Carnegie Mellon University. Aaditya also has worked a lot on multiple testing, among, of course, many other interesting topics. And I am the chair today. My name is Yi Yu. I'm from University of Warwick. The schedule today will be as follows. So we will first have Aharoni presenting, and that will last for about 25 minutes, followed by some quick questions from Aaditya, and that will be about 5 minutes. And then it's Lihua presenting, and then some quick questions from Aaditya. So that in total will be about 1 hour. After that, we will have Aaditya sharing with us some of his thoughts in this general field, and that will be about 20 minutes. And finally, we will conclude this webinar by some discussion from everyone, especially from the audience here, and that will be about 10 minutes. So during the presentations, we would like to ask you to maybe mute yourselves, but you are definitely very welcome to leave the comments, questions in the chat throughout the whole webinar. And please do speak up in the final discussion part. Lastly, the webinar will be recorded. I think you've already seen this. It's recorded and it will be posted on YouTube after editing. So if you do have concerns about this, please do contact us after the webinar, and we will be able to edit the video accordingly. Right, so I guess that's all from me. Aharoni, it's all yours. Thanks.
Thank you. I'll just put up my presentation. Can you hear me?
Yeah.
Okay, very good. So hi, everyone. My title is actually, my original title is the title of this paper from 2014, but I thought it would be interesting and was also encouraged by the organizers to maybe take a step back, and my talk would be more of a retrospective of the ideas and the development around this area of quality preserving and everlasting databases, of which our paper, as I mentioned, was one sort of important building block that we did. Okay, and my talk is going to be very much focused on a wider perspective and on applications rather than the technical details of our work in general and this specific paper in particular. Okay, so what we are thinking about, or what we were thinking about then and have been thinking about since, is this idea of scientific discovery on shared data resources, what we call public databases, which are data resources collected jointly and shared by a scientific community that want to use it as a resource for scientific discovery. So the most basic challenge we're all aware of is how to preserve the statistical validity of the findings that are sort of performed on this shared data resource. And that means to control some measure of overall false discovery of the research done on the shared resource. And if we seriously take this idea of a shared resource that's going to be useful over time, then by definition, the use is going to be sequential. And at any point in time, we're not going to know what the future use is going to be. And so we need some kind of sequential approach to control whatever false discovery measures we choose. And the other thing we want to do, or the way we think about it, is we want to make sure not only that it will be valid, but also that it will remain useful, so that people, the scientific community, can keep using the shared resource in the future and make scientifically valid discoveries over time and continuously on this shared resource. And lastly, very important point is this idea of different ways of doing scientific discovery. So one thing we probably can never assume about the way a shared resource is used, we cannot usually assume that the statistics being measured and the test statistics being used are independent. So anything that requires independence is going to be problematic. But more importantly, we have to think about adaptive use in the spirit of post-selection inference, but this is a sort of a selection that's done ahead of time when we're doing adaptation. So when the future sort of test statistics and tests being done depend on the outcome of previous tests. And that, by the way, automatically means that the tests being done adaptively like that are themselves typically not valid tests. They would not have the right level because they've been chosen based on previous results on the same data. So, and we have to, if we want to be useful, we have to acknowledge that and be able to deal with adaptation as well, ideally, if we want to be really useful for scientific use. Okay. So just to be clear, what I mean by a sequential procedure is every time I see a testing problem, say a p-value, but we can think more generally, some testing problem, I have to do something and give an answer to this testing problem, right? So I cannot wait until all the testing is done before I give an answer. And I want to do this while maintaining that some overall measure of false discovery is controlled. Okay, so the simplest example we can think of is this idea of alpha-spending for controlling family-wise error rate. And alpha-spending is saying we start with a pool of alpha, say 0.05. Every test that we perform takes some of the alpha wealth out of the pool and performs the test at the given level, and then rejects or not according to the p-value compared to the level of the test. And of course, as long as we make sure that the sum of the levels does not exceed alpha, we are controlling family-wise error rate. So rather than doing Bonferroni and dividing equally, we have to divide, we need a diminishing series that also sums to less than alpha, and then we are guaranteed family-wise error rate control. Okay. So the basic notion I want to present to you is one we developed before the JRSS paper, is this idea of quality preserving database. And the motivation we had is in this public database use, if we use something like Alphaspending, then the levels have to decrease and as more and more tests come, because the series has to be converging and sum to less than alpha. And as levels decrease naturally, power also decreases. So if I want to do the same test today at level 0.01 or in a week at level 1/1000, then I would have a lower power. And in some sense, we can think of earlier users as using up, wasting the data for the later users. And so the question we came up is, how can we compensate for use and come up with what we call a stable method, which means that I can do some test and get some power today, and I will also be able to do the same test and get the same power in a week, a month, or a year using this shared resource. Okay, so this is what we call stable. And if I want it to be stable, then I can achieve being stable by not decreasing the level, but I know that I have to decrease levels to, if I'm going to use Alphaspending or anything else, will have to decrease levels. The other alternative is if I increase the data size, and then I get more power at the same level, or the same power at lower level, which is really what we want in our sequential thinking. And so the basic problem is, how can we design payment schemes for usage, which are going to guarantee power to future users and keep the costs down, because otherwise no one will want to use the shared resource and suffer the cost. And basically, our basic paradigm is that this is possible and it's going to be useful and worthwhile for people to use it. So the schematic view of how this works, you do a test, you add data, you do a test, you add data, and you want to do that in a way that guarantees power to future users. So just as an example, which is kind of a canonical example, say we do a stream of normal tests with some effect sizes and power requirement. And what we do is when test I arrives, we have some n samples at that point in our database. We find what C is such that this level, alpha times q to the n, we can think of our current alpha pool as alpha times q to the n, and we need alpha times q to the n times 1 to the minus q to the c to be a sufficient level to obtain the required power. And C is actually going to be the cost, because we will need to add the C samples. Then we're going to have n plus C samples, and we're going to have remaining pool alpha times q to the n plus C. Okay, and we prove in the earlier papers that this guarantees what we call stability, which is our ability to serve an infinite stream with bounded costs. And in fact, the costs are not only bounded, the costs are going to be decreasing. We can show that the bound is decreasing as the rounds progress. And this is just some simulation showing that kind of behavior. So on the x-axis, we have how many tests we've done. On the y-axis, we have the test cost in samples. And we see that typical behavior of diminishing costs as time progresses, right? So what we understand from that is that getting some power for some effect size after 35 tests have been done is not only possible, but it's actually cheaper than getting it when the database is still small. So actually you would not only not lose from waiting, you would gain from waiting in this scheme and doing your tests later. So the basic QPD summary, just very quickly, is that we have a tool for false discovery control in public databases. And we need to add a management layer because in this scheme, you cannot simply give the data to people and tell them to do what they want. You have to do that. You have to control what's being done on your database. And you pay per use naively with samples or maybe with the cost of sample acquisition. And now we can serve an infinite series of requests and we're not going to lose power because the same power is going to be cheaper later. And so far, we've just used Alphaspending to control family-wise error rate in this talk. And one thing we do is we separate scientists from p-values, right? Because our converging series has p-values that are diminishing quickly. So if someone comes in a month, the p-value threshold might be 10 to the minus 50. But it's reasonable to say that we don't actually have p-values anymore because now the validity is the responsibility of the database. It's not the responsibility of the scientist. The responsibility of the scientist is to be able to get some power at some effect size to make discoveries. And we guarantee that they're going to have basically gain more power from as the data set grows. Even though the levels are diminishing, the power is guaranteed to be increasing. So that's all, or the cost diminishing, which is equivalent. Okay, so we can have this graphical schema, which is basically the same thing. We have these two entities, the researcher and the person running the database. And I want to highlight this, what we call the negotiation step, where we have three elements. We have effect size, power, and cost, right? And any two of these determine the third. So a researcher can say, I want power of 0.8 at effect size 1, and I can calculate the cost. And I can tell them that it's going to be cheaper if you wait another week. But in any case, or they can say, I have my effect size I have in mind is 1, and I can afford 100 to pay for 100 samples. How much power can I get to that? And that's a calculation we can do as well. And then once the negotiation is through, we can perform the tests and report results. And the results reported are just reject or non-reject, right? We don't actually report p-values in this scheme. We have p-values, but they don't mean what people are used to think they mean. So we don't really, it doesn't make sense to report them. And now we can publish or not publish or do whatever we want. And the family-wise error rate is controlled over the entire history of use over this database. Okay, I have a use case which I think I'm going to skip over, which is using for replication of genome-wide association studies discoveries. And now I'll move over to talk about basically what was in our 2014 paper, which is moving beyond controlling family-wise error rate. So I'll just give this quick introduction on the idea of alpha investing, pioneered by Foster and Stein in 2007. It's basically very similar to alpha spending, but in alpha investing, you actually get prizes when you reject hypothesis. And now they were able to show that this controls the marginal false discovery rate, MFDR. So false discovery rate is the ratio of the expectations of false discoveries to total discoveries. Marginal false discovery rate is the expectation of the ratios with this adjustment that I'm not going to, it's required to control under the complete null, but I'm not going to get into that. But most important for our practical purpose is that in practice, it requires independence of the hypothesis being tested or the test statistics for the hypothesis being tested. It's not exactly independence, but it's almost independence. So if we want to allow non-independence, alpha investing might be a problem. Let me just show a schema of how alpha investing works. It's quite similar to alpha spending. We have some pool, we draw from the pool, and that determines the level at which we do the tests. The difference is that now we've rejected a hypothesis, and our pool fills back up. Okay. Okay. So summary of our results from the 2014 paper. We examined what combinations of level and reward. So we called it generalized alpha investing because we took the alpha investing paradigm and we asked, there's a specific recipe, what other recipes can we design that take different combinations of the level at which tests are being done and the rewards in case you reject, we reject and take that into account. So we defined generalized alpha investing, which examines what combinations of level and reward are possible and still control MFDR. And we also defined the notion of optimal generalized alpha investing, which is maximizing the expected reward, right? That's the right notion of optimality here, because the more rewards you get, the higher your expected reward, the higher the levels you'll be able to assign your test in the future because you're going to have a bigger pool to use. So, and then we show that, and as I'll show in a minute, the specific variants of generalized alpha investing can be used within QPD, but importantly, this is still under the non-independence. So the relevant level is what we call alpha spending with rewards, which is some variant of generalized alpha investing. The details I don't think are important, but the point is that we can use alpha spending with rewards within the QPD scheme and control MFDR. Right? And we're getting rewards, meaning the cost decrease more quickly. And now, if we're lucky and we get rewards, in fact, we can make the use free. And as long as we keep getting rewards, we can keep the cost free. So let me just show you some simulation. This is a similar simulation to what we had before, and that dotted line is what we saw before, the alpha spending curve, which the setting is slightly different, but qualitatively the curve looks the same. And these are two variants of alpha spending with rewards for controlling MFDR. And we have multiple variants because we can decide how much to pull out of our pool, right? Every test. If we pull a lot and we're lucky, we get big rewards. We reject, we get big rewards, our pool fills back up. If we're unlucky, then pulling a lot can come back to haunt us later. So this is what we call the adventurous version or the optimistic version. This is not optimal, but optimistic is the dashed line. That goes to 0 because we were adventurous and successful and our pool filled up. And from that point, everything is free because it keeps filling up. And this is because it fills up because what? Because good hypotheses are being tested on it, so they're getting rejected. Good alternatives are being tested or good science is being done, we keep rejecting, the pool keeps filling up, and the use remains free. So this is the FDR type behavior where when we have a good hypothesis, it helps other hypotheses as well, right? This is reflected in the cost here. Okay, so I see actually this is not the most up-to-date version of my slides, and I was intending to shorten this discussion because Aaditya is going to be talking about FDR control. So what I mentioned is approaches for MFDR control. There's been a lot of work since then about how to control FDR sequentially, and much of the work is Aaditya's, and Aaditya is going to be talking about it in more detail. I'll just mention that some of these can actually be implemented within our scheme to control FDR within the QPD framework, not only MFDR. Okay, so this was a quick review of the early QPD work and the work that we did in our JRSS paper. I want to use the time I have left to talk about the question of being adaptive and not only dependent. Let me just summarize, emphasize again for this view for our ability to control MFDR or FDR that there's two aspects that make the family-wise error rate alpha-spending version in some sense more relevant for practical work. One is that it allows any form of dependence, and whereas controlling MFDR or FDR does not really allow general dependence structures. And the other one is that the alpha spending system cannot be gamed, in the sense that if someone wants to test some silly hypothesis that's not interesting, they can do it. And as long as they pay the price, it's only going to help future users. Whereas in the MFDR, FDR control, even non-sequential, if some hypotheses being tested are trivial, that affects the validity of the important discoveries, right? So in that sense, the system can be gamed once you're controlling MFDR or FDR type measures. Okay, so I'll talk about being adaptive. So adaptive data analysis is where you decide what to do next given the results of the previous analysis. So now not only the outcomes of the test are dependent, but the tests themselves depend on previous results. And so, for example, they are no longer marginally valid, given that they've been chosen based on the results of previous tests. And so far, we haven't dealt with adaptive tests at all, and I think in general, it's a problem for most of the standard multiple testing approaches. So what I want to do is talk in the few minutes I have left about this approach from machine learning as embodied, or the most famous instance is this reusable holdout work, the science paper by Warwick et al. They showed that with n squared, with n data, we can basically do estimate n squared adaptive quantities. So we choose what to estimate next based on the results of the previous estimates, or equivalently, we choose what to test next based on the results of previous tests. So basically, this can be implemented within an alpha spending type environment to say, I can do n square adaptive tests with n data, and then I'm not able to, my pool dries up and I'm not able to do testing anymore. So this is for sequential, but not, and adaptive, but not infinite. And when we move to talking this computer science differential privacy language, a lot of things change. So the way things are being calculated change. For example, we have this O notation that often hides major issues, such as when we do it in a testing framework, it basically means that we can have very low power because of the big constants hiding within the O notation. But we can still do n squared tests. But if we want to think a QPD version, we have to worry what happens when it runs out and we can no longer do anything. And the other thing is that cost of estimation, which is 1 over square root of n, in the schema, can it be reduced if the users are in fact non-adaptive? And I'll just mention quickly this work that I was a part of, a minor part of, I might add, with people from computer science, for building a QPD-like version that deals with adaptive data analysis. So be infinitely useful, allow non-adaptive users to use it very cheaply, and adapt to the adaptiveness. So be cheap for non-adaptive users, be more expensive for adaptive users, and not have to ask them whether or not they're adaptive. And the implementation we developed basically accomplishes that. So the framework is we charge very cheaply for each query, for each test being done. We return noisy answers, which is like saying we decrease the level of the tests by when we return noisy answers. It's like increasing the non-rejection region. We monitor how much overfitting is being done, which is the essence also of the reusable holdout. And when too much overfitting is being done, we basically charge a large amount of samples. So it's very cheap to use the database, and occasionally it's very expensive. And the nice guarantees that this gives is that users who are non-adaptive, who are naive and just ask questions without using past results, they really get cheap use of the data. So each one costs them on the order of 1 over n. So the order of price is log m for m queries. The adaptive users pay on average square root of m. Why? They also pay very cheaply, but occasionally an adaptive user would trigger this big payment mechanism. So on average, in expectation, they would pay of 1 over square root of m. And the important thing is that we guarantee power preservation and validity for infinite use. Okay, there's major practical issues that I won't go into, but in principle, or in some theoretical sense, we have a solution for the adaptive case as well that's going to be infinitely useful, and it's also going to be cheap if you use it in a non-adaptive capacity, and you do not have to report whether or not you are being adaptive. So I know that I didn't have time to give details, but just wanted to give the general sort of flavor of results we have. Okay, so in summary, QPD is a paradigm for public database management, post-discovery and or publication bias control without loss of power, and the cost is the augmentation of the database size, or in other words, it can be thought of as paying for use. In theory, it can be, or in principle, it can be implemented in practice, and I think it fits well with the ideas of data sharing and also security or privacy, because the data is actually being held in a central location. But there's both cultural issues and practical issues, like the ability to collect more data that's of the same quality or from the same distribution as the data we already have, which might be easy for some cases and might be impossible for others. Okay, and the question of dependence and the question of adaptiveness are questions that we have to deal with if we want to do schemes that are both effective in how they use data and actually useful. That's it. Thanks.
Aaditya, yeah.
Yeah, Saron, thanks. I don't see any questions in the chat. I have some more questions for you later on, so let me quickly ask one question now.
Okay.
Version of your QPD before this NeurIPS 2018 paper you mentioned. Is it fair to say that it's like you're imagining different scientists making different queries, but it's not like the same scientist can make multiple queries to the database because because then they would be adaptive. But it's designed more for the situation where, in some sense, each one can ask a different question and they don't coordinate. Is that right?
I would say so, but also, for science, I think is adaptive in nature. So even if it's different scientists, because the ones who make discoveries are allowed to publish them. I mean, there's not supposed to be any. If there's a hindrance to publishing, then it's not serving its purpose. So in that sense, I think that real science is by definition adaptive. And so, I'm kind of, expressing the limitations of my own work, but I think in general sequential methods have to keep in mind that we have to deal with adaptation. And adaptation, the key point is that it makes your marginal tests or your tests are no longer valid once you're doing adaptive. So I think perhaps we need to think differently and maybe adopt more of the computer science view of how they deal with these things. But I think it's an interesting question for further thought.
Absolutely. Okay, thank you. Yeah, I think in the interest of time, we'll come back to my questions later on and we can move to Lei Hua now.
Okay, thank you, everyone.
Thank you.
Thank you, guys. Lei Hua, right? So,
I'm trying to share my screen.
thanks. So Lei Hua not only needs to get up early because he's in the west coast of the US and he's sick, so maybe I'm feeling very guilty, but I guess that can explain Lei Hua's voice.
Hi everyone. I want to apologize that I've almost lost my voice, but it's my great honor to present my work here. So if during the talk I completely lose my voice, I have another recorded video so I can play. So sorry for that. Yeah. So does everything sound okay? Yeah. So today I'm going to present my work on ADAPT, interactive multiple testing with site information. So this is a joint work with my amazing collaborator, Lei Fithian. So in the usual multiple testing settings, we have a set of hypotheses, H1 to Hn. Each of them has a p-value, P1 to Pn. So here we adopt a standard notation where there's curly H now to denote the set of null hypotheses, and this curly S to denote the set of rejections. And we use R and V to denote the number of total rejections and incorrect rejections respectively. So then the false discovery proportion is defined as the ratio between V and R. And then our goal is to control false discovery rate, which is defined as the expectation. So our goal is to control this FDR at level, say, alpha, say 5%. But as you can see, in many applications, we have more than these p-values. So in many cases, we can observe site information. And in this talk, we will call it xi, and we will treat them as fixed. So one most prominent example is called ordered multiple testing. And here, suppose we can order the hypothesis in an array, and the top one will be most promising. By promising, I mean they're most likely to be null. And then if this is the case, we want to focus power on early hypothesis. And there are also many other examples, like if we have data from similar experiment, then we can get evidence from other experiments. Or if we have spatial temporal locations, then we might expect that the hypotheses that nearby each other should have similar signal strengths. So here, the big idea is if we can learn a region of the covariance space that has many non-nulls, then we can relax the multiplicity correction in that region. And this is not just a toy example. Turns out there are a lot of examples with site information. And here's a great paper published in Genome Biology, I believe, which gives us a lot of generic site information in microbiomics, GWAS, gene set analysis, RNA-seq, among others. So you can see here we have a lot of covariate for us to use. But before, when people just use p-values and Benjamin-Hochberg procedure, this information is lost. So our goal is to use this actual information to help us improve the power. So before talking about our method, so in a nutshell, in this talk, I will present this ADAPT method with full name Adaptive P-value Thresholding. So this procedure is able to control FDR in finite samples under the standard assumptions in multiple testing, which I will elaborate later. And the most important property is that it is robust to arbitrary misspecification of your null. So you can learn a model, but the model can be arbitrarily misspecified. And this method is able to wrap around any black box algorithm and is able to deal with any type of covariate, meaning that your covariate can be continuous, can be discrete, can be mixed types, can be high dimensional. Anything is fine. So before showing you the method, I would like to say that this method has already made impact in practice. So for example, in this Chow and Fithian paper, they show that ADAPT and also its a variant called AdaptGMM has a very good performance across a wide range of applications. Here you can see their ChIP-seq, gene set enrichment analysis, GWAS, microbiome, RNA-seq, single cell RNA-seq. So here, these two rows are given by ADAPT, and the darker this square is, the more powerful it is. So you can see these two rows are very dark, meaning that ADAPT has a good performance. And there's another very exciting paper published in PNAS by Ron Yokuro, Max Giselle, Catherine Rader, Bernie Devlin. So this paper applied ADAPT on multi-omics data with different traits. For example, one trait they are most interested in is the schizophrenia. And they found that if they use a lot of covariates from other omics data, they can find significantly more rejections. So in a nutshell, this ADAPT has already worked well in many applications, and not just by us, but also by biologists. So what is ADAPT? The first thing I'm going to show you is a visualization. So let's say here we have this p-values, and each dot here is a p-value. And just for illustration, let's say we have a one-dimensional predictor X, but in general, we can have any type. So here, ADAPT will start by defining a red region. Here, I use the rectangle, but it doesn't have to be. And then we will define its mirror image, which is 1 minus this red region. So then we will define a false discovery proportion estimator. Roughly speaking, is the ratio between the number of blue points and the number of red points. And the intuition is because under the null, the p-value is uniformly distributed. So roughly speaking, the number of blue points would be the same as the number of red null points. And then we will update the threshold until this FDP hat is below alpha. So you can see that you can view this FDP hat as a monitor and tells us when to stop. And when this holds, we will stop and reject everything in the red region. So this is the visualization of the method. But what I haven't told you is that how to update this threshold curve, which is this red curve. So as an analyst, the view of this analyst is slightly different from what I showed you before. So from an analyst view, we can only see this partially masked p-values. So recall, previously we have this blue dots, red dots, and black dots. So at every step, the analyst is able to see all the black dots. But instead of seeing the blue and red dots, they can only see the pair of P and 1 minus P. So in other words, for each dot here, we will see 2 dots, but we don't know which one is. So for example, you see here, there's a red dot, but here we can only see this purple dots together with this mirror image. So what we are going to do is we can use all information that can be observed in this figure to select the net threshold. Mathematically, we can use all the covariates, and we can use all these partially masked p-values. And we can use that to keep updating the threshold. And more importantly, as we move on, you see more and more dots become black. So instead of seeing a pair, we can see this p-value itself. So that means as we move along, we have more and more information. So what's crucial about this is that as long as your update rule is measurable with respect to this, any such rule is okay. So the intuition behind it is simple. So we have this covariate, we have this p-value. Of course, intuitively, we want to use this covariate and p-value to learn something. So for example, we can look at the covariate and see in which region there are a lot of small p-values. But if we used all the information, then we will definitely overfit. And that will violate any error control. And this partial masking is a way to protect against overfitting. So we mask some information from the analyst. But turns out what we are doing is just to mask one bit of information. So we don't mask all the information. And by revealing this, we still have a lot of information from the data. So our main result is the following. Suppose that conditioning on the covariate and the non-null p-values, if all the null p-values are independent and mirror conservative, which is a new concept we define in our paper, you don't need to worry about this concept. One thing is, if the p-value is uniform, it's mirror conservative. So this is just a generalization of the uniform distribution. And we show that a lot of most examples in the practice satisfy this property. Then we show that adapt controls FDR at level alpha in finite samples. So here, note that the non-null p-values can be arbitrarily dependent, and adapt controls FDR with arbitrary update rule. So I want to further emphasize on this, which is adapt is unusually flexible in that the FDR is controlled no matter how misspecified our model is, no matter how misguided our priors are if we are using a Bayesian method, no matter how we select the model or tuning parameter, and more importantly, no matter how crazy we are. So the thing is, don't worry, use your favorite method. You will always have guaranteed FDR control. But there's never free lunch. So another side of the story is, don't be too crazy. You should always use the best available method. Otherwise, the power will be degraded. So in summary, on one side, you can use arbitrary model. You always get FDR control. So you always get type 1 error control. But we always want to gain power. So we need to use a good model. And in next few slides, I'm going to talk about what we mean by a good model. Okay, so that's about flexibility and FDR control of this procedure. The next question is, how are we going to train a good model to update the threshold? So here, the guiding principle is we need to use local FDR. So in our paper, we show that under the two-group model and mild assumptions, the optimal threshold should be a level curve of the local FDR in our setting. So a similar result also appeared in previous works, but when you use our FDP estimators, we also have the same observation. So this result gives us a general principle. So what we want to do is we first propose a working model. By working model, we mean that this is a model you believe, but it doesn't have to be true. Then you use your favorite method to fit the model, and then you estimate the level curves of local FDR. And what you can do here is that you can move the threshold towards a near level curve. So like in classical method, when we estimate local FDR, we will directly move to the point where this local FDR is controlled. But here, because our method is iterative and we have such a strong FDR control guarantee, so we can be patient. And what we can do is we just move the threshold a little bit towards a near level curve, and then we repeat these steps to refeed the model. Because as you recall before, as we move along, more and more points turn black. So initially, we mask a lot of p-values, but in the later stage, we observe more information. So this allows us to fit a better model. So what we want to do is we want to fit this model and be patient and refit until we get a better and better model, and we will stop until FDP hat is below alpha. So let me give you a concrete example. One working model that we found very useful in our applications is the simple conditional two-group model, where we assume that conditional xi, this indicator of being now and now is a Bernoulli random variable with a potentially covariant dependence mean pi 1x. And we assume that conditioning on that this is a now, it has a density f now. Conditioning on this is now, it has a density f1, and we allow both f now and f1 to depend on x. So this model is very flexible. Like in other works that involve two-group model, you usually see that they allow for this Bernoulli parameter to depend on x, but usually they assume a common f now and f1. But here, we also want to assume a dependence on x. But once again, I want to emphasize that we don't need this model to be correct. It's just a working model. So here, to further simplify, we assume that now density is just uniform. And then we can define the mixture density, which is just mixture of f now and f1. And then we can recall the definition of local FDR, which is the probability that hi is now given both the covariant value and the p-value. So what you can see here is that it is basically 1 minus the proportion of now divided by the marginal density. So again, if the Bayesian model is correct, then we can define local FDR. But in general, in the frequency sense, this local FDR is not easy to define. But here, we just rely on this concept in the working model. So what we know is we previously showed that the best threshold should be level curves of this local FDR. And we know that it has a closed form expression. So if we can estimate this local FDR, then what we can do is we choose the next level surface. But as you can see, here we have a missing data problem, because in this setting, we don't know what hi is. And also we have a masking. So for many p-values, we can only observe their minimal p and 1 minus p. So if we were to observe both hi and pi, then we can easily fit this mixture model. But here, we don't have that. But we can easily use the EM algorithm. So you can view this as a missing value problem with two levels of missing. One is hi, one is pi. So if you start with a model, you can compute the posterior for both pi, given minimal p and 1 minus p, and also hi, and impute that. And again, although EM algorithm that doesn't it's not necessarily working in theory, but here we don't need that to work in theory because this is just a working model. So here is the pipeline for this EM framework. So at every step, we input the covariate and partially masked p-values, and we first pass it through the E step to do the imputation. We impute hi and pi. And then we fit the local FDR. And in this step, we can use any fitting algorithm. We don't necessarily using the classical EM. We can use, say, JLM, GAN, GBM, Lasso, random forest, neural networks. Anything is fine. And then we see whether it converge. And if it is not, we iterate on that until convergence. So if you cannot afford a lot of computation, you don't then you output the current estimate. And now for each hypothesis, you have this local FDR estimate, and you can use that to choose the next level curve. So overall, the whole pipeline for the adapt is the following. So we input the covariate value and the p-value, and at each step, we mask the p-values that are either red or blue, but leave all the black dots revealed. And we pass that into an EM framework. And what I didn't have time to talk about is that we can also allow for model selection. So suppose you have different models, or suppose you want to fit a spline model, you want to choose the number of knots, you can still do that. And once you get the local FDR estimate, you update the threshold and the rejection set, and you check if the FDP is below alpha. If no, you go back and iterate. Otherwise, you return this rejection set. So that's the procedure. And here we have our package called AdaptEmpty, which is available on CRUN. And in this package, we implement quite a few convenient wrappers using GMM, GAM, GleamNet, GBM. We also provide a generic interface that allows any user-specified learning algorithm. So I know that there are also other works that build on top of this package using some other algorithms like GMM, like XGBoost. So you can easily apply this package to your own problems. So here I'm going to illustrate our method on a very simple and old-fashioned data set, which is an RNA-seq data. And this data gives the gene expression levels in 2 mouse strings. And in this data, we have about 14,000 genes and 21 samples, 10 in one group, 11 in another. And our null hypothesis is that there's no differential response in gene I. And here our p-value is computed using the DSeq2 package. And our covariate is the logarithmic normalized count, again using the DSeq2 package. So I don't have time to talk about detail of this covariate, but this is one of the standard covariate used in this context. So this data is from this Bottomley et al. Paper, and we follow the same way to study this data by Ignatiadis et al. So here is an animation of our method. So you see that here each black dot, which is very tiny, is a p-value, and the x-axis is the logarithmic normalized count. And from the domain knowledge, we should expect that the larger this x is, the more likely we should reject this gene, because that gives us more evidence. And you can see that our method is iterating on this threshold curve. Let me repeat it. And you can see at the beginning, it will fit this local FDR. You see that this local FDR fit is still a little bit noisy, but it's quite stable over time. And we keep updating it, and you see it goes down and down, but this monotone pattern is kind of persistent. So in other words, we kind of learn the pattern in this data. And you see as FTP hat goes down, so here, let's say our target level is 5%, we find about 600 rejections. And one more thing is you see that this local FDR estimate looks very stable. So in the end of the talk, I will give you slightly more explanations on why this is the case. Okay, so let me stop this movie. Okay, and here's a power comparison. So because there's so many great methods that can work in this data, some are using the covariance, some are not. So we did a very serious comparison. So here you can see we include about like 12 methods. Oops, I couldn't see my cursor. Anyway, so in the lab panel, we have about 12 methods. And I know it's hard to see all of them, but you can see there's one red line standing out in terms of power. So here the x-axis is the target FDR level. The y-axis is the number of rejections. So usually, if you have a higher number of rejections, we tend to think you have higher power. So you see that the red line is our method. So we can significantly gain in power by using the covariate, by using the side information. So in the right panel, you can see that that's the final rejection curve, which is monotone. And here you see some weird kinks, but that's because we are using the spline method. But if you are using some other method like gradient boosting, the curve is going to be much smoother. So in the last few minutes, I'm going to briefly talk about why you get very stable local FDR estimate. So recall that we use this partially masked p-values. So even in the initial step, we can observe all the covariate at minimal p and 1 minus p. So this is already a lot of information. For example, if you observe that the minimal p and 1 minus p to be 10 to the minus 8, that means this HI is most likely false, because compared to 10 to the minus 8, the chance that you get a p-value as large as 1 minus 10 minus 8 is very small. So that means even if we mask one bit of information, this doesn't really remove that much information in the multiple testing context. And also, as we move along, we get more and more information. So in the end, this filtration FT is almost the same as the whole data set. So it has nearly no information loss. And this is much more informative than just using the large p-values as in some other methods. So here is a plot showing the correlation of the local FDR estimate as alpha moves from large to small. So you see that even initially, the correlation is as high as 99% in our data. So that means even initially, our local FDR estimate is pretty precise. So that's pretty much about ADAPT. And of course, we have we didn't stop there. So later on, we extended this ADAPT to other settings. And one example, which I think Aaditya is probably going to talk a bit about, is FDR control with structural constraint. So for example, you might do multiple testing to try to reject the set, which is convex. Or you might do hierarchical testing, where the hypotheses are on a tree, and you want to reject a subtree. So here, we have this star algorithm. Oops. Okay, I don't know if I can play this video. Anyway, so in the left panel, we have this convex region detection. In the right panel, we have this tree testing. And also, we have another setting where suppose we don't have this unidimensional p-value, but we have multivariate test statistics. So in this case, it's not easy to sort the p-values. But we have another procedure called bags of null statistics, or bonus in short, which can take advantage of the multivariate statistics and try to learn the most promising direction for us to do the multiple testing. So just to wrap up, in this talk, we proposed the adaptive p-value thresholding procedure, or ADAPT in short, which controls FDR in finite samples under the standard assumption in multiple testing literature, which is robust to arbitrary misspecification of non-nulls, and it can wrap around any black box algorithms and can deal with any type of covariate. With that, I would like to thank you all for your attention, and thank you for your tolerance on my voice.
Thank you very much, Leo. That was an excellent talk as well. Again, I don't see any questions in the chat at the moment, but let me ask a quick one and then we'll return to some more later on. So do you have any thoughts about, before actually running the ADAPT procedure on the data, how one can even pick a model class? Like, is it is it? Do you think it's possible just using only the masked p-values and the covariates, but without actually running the procedure at the start itself? Is there enough information to choose between types of models to be fitting?
That's a great question. I think usually yes, because so in this AdaptEmpty package, we start from 0.45 for the rep region, but later on in the follow-up paper by Lei Fithian, they found that we don't need to start that high. So they start at level, say 0.05 or 0.1. So that means you already have a lot of information. So what you can do is you can simply use the initial sigma field and try a lot of models and pick the best one. Yeah. And later on, as T goes large, it's basically like a surgery. So you make some slight modification on your existing model, but most of the model selection should be in the first step. Yeah.
Yeah, I think that makes a lot of sense. Yeah. Thank you, Lihua. I think for now I'll go ahead with my discussion, and then I'll come back at the end with some more questions for both of you. Okay. All right, so you should be able to see my screen. I'm Aaditya Ramdas, I'm at CMU, and it's my pleasure to discuss two very influential works, influential in my own line of work, but I think very broadly influential as well, by Aharoni Rosset and by Lei Fithian. Okay, so what I'm going to do is I'm going to describe some broad motivations for these works, maybe broad, slightly different from what the authors mentioned. And I'll mention how each of their works has spurred, a line of future work and what these future works have done. And then we'll ponder a little bit about future directions. Okay, so let me first start by saying that the word sequential is heavily abused because anything in which there's a notion of progress happening in multiple steps, people use the word sequential. That's very natural. But now what we're going to do in this talk and try to make sure happens in the literature is that we use different terms for different settings. Okay, so we're going to use the word interactive, even though this, the ADAPT algorithm was also sequential in some sense. We're going to call it an interactive algorithm because it has a fixed data set and it has a fixed set of hypotheses. And it's the analysis that's really sequential in nature with a human in the loop, and that's going to be called interactive. The usual word sequential will be left for settings in which there's a single experiment and you're collecting more and more data for that experiment. This is like the sequential probability ratio test. Since Wald gave it that word sequential, we'll stick to that word sequential. In other words, the hypotheses are fixed. It could be a single or multiple hypotheses, but you're increasing the amount of data for those hypotheses. So you can have sequential multiple testing problems in which you're collecting more and more data from different hypotheses. And so I'm going to use the word sequential only for that. And the word online is going to mean something else again. And online testing of hypotheses is the number of hypotheses is itself increasing. So in the first two, the number of hypotheses is fixed. But in the online setting, the number of hypotheses is increasing. And you might have a fixed data set like a quality preserving database, or you might add to that database, or you could have completely new data. The exact setting can vary, but the important difference is earlier, I think all of these, many of the papers like SeqStep called the original thing sequential, and then sequential multiple testing has now been called online multiple testing. But I want to disambiguate these three. I think that's quite important for the field going forward to know when someone says sequential what they mean. Okay, so it's interactive, sequential, or online, different problems, and each of these corrects for a different notion of selection bias. So the first one corrects for analyst freedom and double dipping of the data and things of that kind. The second one typically corrects for adaptive stopping or continuation of an experiment. And the third one corrects for selecting which subsets of experiments or hypotheses to count as interesting and report them. Okay, so with that terminology out of the way, let me quickly discuss the generalized alpha investing work by Aharoni and Rosset. So I think of science generally as being like a sequence of sequential experiments. So if put yourself in the, like imagine yourself being Novartis and trying to test for drugs that cure Alzheimer's or diabetes or something of that kind. This is a decades-long process. Many different drugs will be tested over time. Some of those clinical trials. So here on the y-axis, I have experiments, so you can think about them as being different drugs. Y-axis is the number of samples collected. So each bar over here is like one clinical trial, and so you might have short ones, or you might have really long ones. You might have several starting at the same time, and so this might go on forever. We have no idea when we'll find a cure for any of these diseases. This might go on for a long time. In the tech industry, this is actually exceedingly common. The A/B tests are run all the time. Actually, like tens of thousands of A/B tests are being run by Amazon and Microsoft every year, and they're broadly sequential to sample tests. Okay, and so each test here is a sequential test. So if I look at any one experiment, that's a sequential experiment. But if I zoom out and I look at the sequence of experiments, that's an online testing problem, because different hypotheses are being tested over time. And the same when you have different treatments and a common control. These are different treatments, they are different hypotheses. So the number of hypotheses is growing over time, and data is also being collected within each sequentially. So there's a doubly sequential thing going on here, and we call the outer process online, just to differentiate it. So that's the online multiple testing problem. Okay, so I'm just going to use the example of internet companies. They test to see whether changing the color can improve people's engagement with the website. They might see whether changing some icon makes you shop more, and so they're running thousands and thousands of these tests over time, and that's a big problem. If every one of these tests is run at level alpha, that's a problem. We know that from basic multiple testing. So the question that one can think about is, given a possibly infinite sequence of tests or p-values, can we control the FDR in a fully online fashion? And what that means is now we're going to have to give a different level alpha 1 to P1, different level alpha 2 to P2, and so on. Okay, so the question is, how do we set these error levels in order to control the FDR at any time? Okay, so FDR, or the modified false discovery rate, as Foster and Stein did, or as Aharoni and Rosset did. So you can choose your error metric. But the point is, we have to set these error levels in an online fashion, and these decisions are irrevocable. So you can't go back 100 steps and say, hey, the change you made to your website 3 months ago that was a bad mistake. So in some sense, once you've paid the price of making a change to your website, that decision is irrevocable. And offline FDR methods don't yield this type of a guarantee. So that's why we need a new class of methods. Okay, so this is like a cartoon picture of what we might hope to achieve. So this is from left to right is time, and you have this overarching online FDR control procedure that's telling all the experimenters what to do. And every time you start a new experiment, which is like a red box, you get told an alpha level for that running that experiment. Okay, and how that alpha level will be decided by the online FDR procedure that is trying to maintain the FDR at a level alpha. Okay, so alpha j will change with the experiment. And then you can have a multi-arm bandit algorithm. Maybe if you have multiple treatments, you can be assigning them adaptively. You can peek at your data as this is going on. So this entire red box is abstracted away and saying this is the sequential aspect. There's data being collected sequentially. That's abstracted away. At the end, you get a p-value, you get a rejection decision. Did I make a decision or not? Okay, so do I have enough evidence to reject the null? So I get a 0 or a 1. The online FDR procedure updates and gives the next experiment that starts a different alpha level, and so on. So that's kind of what we're aiming towards. So all online FDR procedures kind of work, in the same kind of fashion. As different experiments start, you start off with a big error budget, and then you spend your error budget on different experiments. But the nice part is that your wealth doesn't always decrease. Every time you make a discovery, you gain back some wealth. And so the error budget that you use for each experiment is data dependent. And this is an infinite process that keeps going on. You keep losing wealth as you test nulls, and then once in a while you test a non-null, you gain back wealth, and so on and so forth. Okay, so here's a little bit of a history of how this area has proceeded. Foster and Stein conceptualized it in their RSS 2008 paper. They called it alpha investing. Aharoni and Rosset, talked about quality preserving databases and generalized this alpha investing algorithm. Then a few years ago, it really picked up in the last few years, but Javanmad and Montanari came up with a different algorithm, LORD, which first they proved that it controlled FDR, not the MFDR, and they were the ones that went away from the quality preserving databases motivation to this kind of a repeated different A/B tests kind of application. That's the one that they mentioned. Soon after, it was realized that LORD can be improved to LORD++ for free. Essentially, you can get strictly higher power than LORD by a small improvement. So that algorithm was called LORD++. But more than that, it introduced a different perspective on how to design algorithms, and that's what I'm calling the Oracle perspective on designing algorithms. Then that new perspective on designing algorithms led to the creation of new algorithms. One of them is called Saffron, which is adaptive to the underlying null proportion. So you think of this as an analog of the StoryBH algorithm for the online setting. And then if you're familiar with StoryBH and you try to adapt to the null proportion, if you have conservative nulls, you'll actually hurt your power. That's the behavior of StoryBH. And so ADIS stands for adaptive discarding, and you can actually discard conservative nulls and gain power when you have conservative nulls. Now there's versions that you can go in between the online and the offline setting. So there are mini batch versions where you can start batches of experiments, and in each batch you want to run a BH type algorithm, and then across the batches you want to run an online FDR type algorithm. And so there's these algorithms that now can interpolate between offline and the online setting and like recover BH if there's one batch and recover LORD or LORD++ or whatever if there's multiple batches. If there's each batch is of a single experiment. And so they have these mini batch style algorithms. And now these can be run completely asynchronously. The version I told you is it's one experiment after the other. But what if there are experiments starting and ending at different times and multiple experiments running in parallel, and some have stopped and some haven't, and so on. So you can do this completely asynchronously, but you can also handle some kind of local dependence between these different experiments that are running at the same time. And finally, like the earlier works, they focused on FDR control at fixed times, but in a natural online setting like this, you might be interested at stopping times, like the time of the 100th discovery is a stopping time, and then you want FDR control also potentially at stopping times. But there's been a lot of work that's extended this beyond FDR, the error metric of FDR itself. One might say, well, when I'm at time 100,000, why do I care about what happened at time 1 or time 2? And so you can say, I want to forget the past. And so you can extend FDR to this notion of decaying memory FDR that smoothly forgets the past. And you can adapt all of these algorithms to take into account this decaying memory. You can extend these to estimation instead of testing. So if you don't want to do false discovery rate, but you want to do false coverage rate or false sign rate, then there's LORD CI/CI for confidence intervals. And you can also do this for prediction intervals. So if you want to do conformal prediction style prediction intervals, but you want to be selective about which points you cover, then there are adaptive variants of these algorithms that work for estimation and prediction and things of that kind. You can do post hoc inference, like simultaneous post hoc bounds on the false discovery proportion. That's been another exciting upcoming area in the multiple testing literature. And I already mentioned that the stopping times property, and then you can extend these to family-wise error rate as well. So you might think that Alphaspending is the only natural algorithm for family-wise error rate control, but that's not true, because if you assume that there's some kind of long-term independent structure, which means that the 100,000th test is not dependent on the first test, there's a little bit of independence there, then you can exploit that and develop algorithms that are much better than Alphaspending. And then there's actually quite a bit more. There's empirical Bayes methods developed by Wen Sun, extensions to discrete settings recently by Sebastian Doller and Etienne Rocaine and others. Lower bounds in a Gaussian sequence model by Eddie Arias-Castro and Chen. And excellent software being developed by David Robertson. There's an online FDR package on which you can try a lot of these methods out. Okay, so there's, as I mentioned, there's two viewpoints for online FDR control. The earlier work was this algorithmic viewpoint. To define an algorithm, we must specify how much wealth we start off with, how much wealth is subtracted on testing, how much wealth is awarded for each discovery, and then prove that for these choices, FDR is controlled at level alpha. So this is a very algorithmic way in which the original algorithms were developed. But now we have switched to a statistical viewpoint. So the statistical viewpoint is now, instead, to define an algorithm, what we will do is we will design an empirical estimator of the FDP. Let's call that FDP hat. We will prove a lemma that says if you keep FDP hat less than alpha, then it implies that actually FDR is also less than alpha. And then we design algorithms that can keep FDP hat less than alpha. And so essentially all of the advances that have been made. You can view Lot++ as an online version of the BH algorithm and Saffron as online story BH. These advances have happened basically because we've now really written down what is the empirical estimator of the FDR that's being used implicitly in these algorithms. Can we design a better estimator of the or FDP hat, and that yields new algorithms. So that's why these advances have happened recently. Okay, and so let me end with some this first part with some questions for Saharon. I was wondering if you had any thoughts on hierarchical or multi-scale notions of error for large organizations. So imagine you're Novartis or you're Google, and you're running these kinds of experiments. Maybe you have one branch doing diabetes experiments, another branch doing Alzheimer's experiments, something of that kind. You have different groups, and you as Novartis care about not having too many false discoveries. By false discovery, this might mean pushing things to a second stage clinical trial. You don't want too many false ones. If you're Google, it might mean that every time you reject a null, you make a change to your system to incorporate that new discovery that you've made. So you don't want to make too many false changes to your system, which would be just wasted money and effort. But now, how do you incentivize different groups that are experimenting to cooperate with each other? Like one group could say, why should I pay for the other group's excessive poor testing? And so, each group might think they test very sensibly, but the other group is wasting the alpha. Like, how do you have any thoughts on how one can, set up these kinds of incentives? And the other question was about quality preserving databases. Are people already using quality preserving databases in some subfield in medicine or at IBM? Because I know that your co-author Aharoni is at IBM. So if yes, where are people using them? And if not, why not? Are the remaining limitations, are they practical, that is software or incentives or awareness, or are they theoretical, that is we don't know how to solve some relevant problem? Okay, so let's return to this after I discuss Dihua's work, which was ADAPT. And so I think this can be motivated by thinking about, is there a reproducibility crisis in science? This was a survey taken by Nature in which they found that there's actually a significant fraction of the thousands of researchers surveyed from multiple different fields that felt there was a reproducibility crisis. And one of the reasons for this, I think, is the researcher degrees of freedom. So data scientists, when they have a data set, they want to interact with their data. They don't just fix a method before looking at the data, apply it once and are done with it. They never do things that way. So they want to interact with their data. They want to use their intuition. They want to use their priors, and they want to exploit the structure in that data. Okay, so all of these are things that they want. However, many classical statistical methods were not built to handle this type of interactivity. And so there's a need for principal statistical methods that actually work in interactive settings. And the key idea behind ADAPT is that if you mask the data appropriately and then peek all you want at this masked data, then you can be protected from overfitting and selection bias. And I think that's a very important idea, is that the amount of masking is negligible. Like in ADAPT's case, there's only 1 bit per p-value that's hidden. Most of the p-value is revealed. And that's kind of enough to allow the user a significant amount of flexibility while running the algorithm. And that's a very nice key insight that appeared in this paper. Over time, the user can progressively unmask the data 1 point at a time and improve their models as they go along to improve power. And this is, as long as an appropriate martingale type test, the underlying theory behind ADAPT is based on a particular martingale, and so as long as that's used, everything will still be okay. So I think very interesting idea. There's, I think, plenty to do in future work. And so one example of this was masking the p-values as mentioned. There's the minimum of p and 1 minus p is revealed, and then the missing bit is kept hidden. One is used for selection, the other is used for inference, and so you get correct post-selection inference regardless of the interaction. So this work has also, spawned a lot of interesting follow-up work. So they first conceptualized masking, and this was the first interactive FDR method. Soon after, we generalized this. This was joint work with Dihua and Will, but we generalized the notion of masking. So the previous slide had one example of a masking function, but it turns out that there's a huge class of masking functions that you could use for these algorithms, and they have different, benefits and trade-offs, and you can impose constraints. So if you want your final output set to satisfy some constraints, then the star algorithm can achieve that. You can say, move away from FDR control. You can have interactive tests for testing the global null. Again, the advantage is you can use covariates, and you can use your prior knowledge, and you can do all of these things, but still get correct type 1 error control for global null testing while maintaining interaction. You can extend this to family-wise error rate control. I think one thing I'm going to briefly mention on the next couple of slides is you can move away from classical testing problems and move towards causal inference. And you can do rank tests by betting, and you can do identification of individuals that have positive treatment effects interactively. So I think this might give a new kind of class of applications outside traditional multiple testing where these ideas are applicable. But there have been even further. Lihua mentioned this bonus algorithm, which uses an empirical based perspective and does not work on p-values. It works on raw data. Same with the causal inference applications. They don't have p-values. They work on raw data. So you can mask raw data without having p-values as well. And that's basically the important takeaway message that I want to mention here. And recently there have been applications to omics as well. This is by Ron Yurko and Chow and Fithian. And so there's a lot of interesting applied work being done in genetics, but I think these ideas would be applicable in other settings as well. So if you ask with interactive causal inference, like what does that even mean? Like how, what are you trying to do? The idea is very simple. You can mask the treatment assignment and try to guess it. So if those of you are familiar with causal inference, you usually have covariates, outcomes, and a treatment assignment indicator. Was this person treated or were they controlled, for example? And so what you can do in this masking framework is you can reveal to the data scientist all of the covariates and the outcomes, and you can leave one bit missing. Was this person treated or controlled? And they have the same role as in ADAPT. And the intuition is, if you can guess whether a person was treated or controlled from the covariates and the responses, then there must be a treatment effect. If there's no treatment effect, you're going to be randomly guessing who's treated and who's controlled. So that's the basic intuition behind why this masking is related to causal inference at all. Let me give you a more concrete example so you can visualize some, like I think Lihua gave some beautiful visualizations of multiple testing applications. Here's a causal kind of setup. So here I'm showing you two covariates. Imagine age and weight as your two covariates, X1 and X2. And what I'm plotting on the left are the treatment assignments. Of course, the data scientist doesn't know this. This is for you, the audience listening, which means like the purple ones are treated, the orange ones are controlled. So like this population, half of them, every box is a different person, and half of them were treated and half of them were controlled IID. Okay, so this is a randomized clinical trial for simplicity. And each person has some potential treated outcome and a control outcome. And obviously, we don't observe both of them. We only observe one of them. If the person was treated, we observe their treated outcome. If the person was controlled, we observe their control outcome. So these are the actual observed outcomes that you see in practice. So now at the bottom left is small values 0, at the top right is large values 9. This is what you actually observe. On the right, the data scientist actually sees this, okay? And we mask the treatment assignments, the things on the left. Now the question is, from the thing on the right, if I ask you to guess which people have a positive treatment effect, which subjects have their treatment effect larger than their control, okay? This is like individual level inference. This is a very subtle question because for any given individual, you either observe the treatment or the control. You don't observe both. But the question I'm trying to ask is which individuals have one greater than the other, okay? So that's an interesting question. And let me show you the truth, the underlying ground truth. I mean, if you looked at this plot, you might think that the truth is in the top right. People with larger outcomes maybe have a treatment effect, but it turns out that the truth is actually in the middle. Just to show you how subtle it is to try and guess who are the people that are responding to treatment. And the interactive algorithm, we call it I-cubed. It actually does have very good power in identifying who are the individuals, and it has an FDR control guarantee despite the interaction and so on. So I think. If you find that curious, I'll let you check out the paper. Here are a couple of questions for Lihua. So I think dependence is a major issue for ADAPT. I think, unfortunately, it's very easily anti-conservative under positive dependence, unlike Benjamin-Hochberg. And I was wondering what advice you have for practitioners on this front. So for those of you who are not familiar with what I'm referring to, positive dependence, there's this experiment that, we ran in which there's, 40,000 hypotheses, and the truth is the stuff in black, and the gray is they are nulls. This is what Benjamin-Hochberg does, because the covariates are the XY coordinates of the null and non-null, and the BH doesn't use the covariate, so it doesn't have very good power. But star or adapt, they will have good power, and they will identify these regions really well. So these are powerful algorithms. But when you try them out on positive and negative, so when you have independent data, that's the first row, circle in the middle, circle in the corner, they all have FDR control at the target level, all the methods, that is star, BH, adapt, things like that. But when you move to positive dependence, it seems like BH becomes conservative, star remains reasonable, and adapt becomes anti-conservative. So that's a little bit worrying. Under negative dependence, all of them are doing reasonable jobs. Okay, so this is what I mean by adapt becomes anti-conservative under positive dependence. And so I wonder if there's any advice you have for practitioners in terms of pre-processing so that you can make things somewhat independent or something of that kind. And another question is, a lot of this work was motivated at the start by some kind of reproducibility goal. Hopefully people can interact with the data while getting FDR control. But the problem is that at least BH gives you the same answer every time you run it. But for adapt, if it has low power, then a scientist could kind of blame it on the model or the exploration strategy, and they could quietly rerun it on a different model, but not really report how many times they tried different models and exploration strategies before they finally reported the results. And so like a different type of reproducibility issue might arise. And so the question is, how would we know what they tried, and how can we stop this from happening? Or what are your thoughts about the effects on reproducibility? Okay, so with that, let me end. I will stop sharing my screen and let Saharon and Lehua respond to these questions.
Thanks for the so fascinating discussion, Aaditya. Maybe it's better you still share the screen. Just
okay, so that they can.
Yeah. So yeah, maybe if Lehua doesn't mind, maybe Saharon first.
Let me just go back.
I'll be very quick. Very interesting questions, but I think we can answer them pretty quickly. So the first one is about incentivizing people to share data, and the really attractive scheme, especially of our first basic UPD framework, is that you don't care if people are doing good science or doing bad science. You're still going to gain from the fact that they're doing science and paying, that they're testing and paying the prices. So actually, you're highly incentivized to have all the lousy groups sharing the data with you. This is under the assumption that more data can always be purchased or supplied, right? Which is problematic assumption. And you can also, in the more advanced, say, investing approaches where you do care if good science is being done on your database, you could definitely imagine that you're carving, you're pre-carving your pool, or you could argue that different sub-communities don't care about jointly controlling MFDR and each can control its own. But when you're doing alpha spending and the basic UPD scheme, you're just going to be gaining from all the less smart than you people who are also using the database. For the second one, yeah, I'm not really aware that people are using QPD, and for a while I was quite dismayed by that. I know that Yoav Benjamini is also a big proponent of QPD, and we've been talking to people. But if the question is whether the concerns are mostly practical or theoretical, I would say that it's mostly theoretical. So one thing that I don't know if it's practical or theoretical is people have a really hard time disconnecting from p-values. Another major concern, I think, that actually runs through everything we've talked about here is worrying about dependence and especially adaptiveness. And if you don't have answers for that, then then it's kind of difficult to really popularize the approach. And people are saying, we know that it's adaptive, then we're going to suffer the cost of collecting new data every time, but we know that we don't suffer from the adaptiveness issue. That's my limited perspective on why it hasn't been really adopted.
Thank you. Liwa, do you have any thoughts?
Yeah. So Aaditya, I think.
And sorry, Liwa, I just want to thank you, Aaditya, for your really, as usual, whirlwind and very informative presentation.
Thank you.
Yeah. So for dependence, first, independence is a real issue for us. And that is main motivation for one of my following work with Lei Fithian on dependent adjusted BH. Because we know that when you have dependence, the adapt tend to be sensitive. But on the other hand, if the dependency is not too strong, so for example, in the plot you show us, I believe that's an equicorrelated case with correlation 0.5. So that's like a multiple comparison to control problem. So in this case, you may be problematic, but if the dependence is short range or weak, I think adapt is still quite robust. But on the other hand, there's another interesting thing, which is the model itself has some interaction with the robustness to dependence. So suppose your model doesn't pick up the local random effect, then it can be more robust. So actually we have an example showing that comparing adapt without any model versus with a model, then turns out the one with model is more robust because somehow, so for example, if you have a local cluster with high correlation and they happen to be that all the p-values are small. So if you're using adapt or BH, they will pick it up. But if your model kind of using the side information show that this cluster is not promising, then it will not prioritize that. So that's why the model itself can be also important. And so that's about the dependence. So then for your second question, that's also an excellent question. Oh, all right. Okay. Now I think I'm connecting again. So I think reproducibility has a very broad definition. So it doesn't really mean that everybody should get the same result. Because even if you are running BH, you have lots of ways to hack it. You can select samples. You can choose different ways to compute p-values. You can do a lot of things to make it not reproducible. So I think adapt here is adding one more exploration step to make things more flexible. But eventually, I think as long as you're using a principled way to update your threshold and you show other people your code, then it's still satisfying this reproducibility principles. So in principle, we can also make adapt human in the loop in the sense that every step you pick the threshold in arbitrary way you like. That's guaranteed by our theory, but we don't advocate that. So instead, in our package, we always use this algorithm-driven way to select the next threshold. So that's the motivation for reproducibility. And sorry for the connection issue.
Yeah, no problem. Luckily, your last two answers, we heard them perfectly clearly. I do want to open it up to the audience to see if there's any questions. Unfortunately, so far, there haven't been any posted. I'm done with my questions, and I'm happy with the excellent answers that both of you have provided. Let's wait for 20 seconds to see if anybody mentions anything or raises a hand.
Yeah, at the same time, Liwa and Aharoni, if you want to comment on each other's works, it's all Aditya's discussion. It's also time.
So I have a question for Aaditya. When you talked about the development for FDR, which is, impressive and really interesting, you mentioned that this goes on and on, but it's actually not infinite, right? unless you make sure to carve your, either you're lucky and it fills up, in which case it can be infinite, or you make sure to carve it into smaller and smaller pieces, then it's not by nature an infinite process.
Yeah, that's right. I mean, it's meaning you will, if you test 10,000 nulls in a row and don't reject any, you will be testing smaller and smaller alpha i's. In that sense, you are losing power. But the decaying memory FDR actually gets rid of some of those problems, in the sense of when you slowly start to forget the past, you actually are also forgetting the nulls that you tested repeatedly. And it actually constantly gives you back some older wealth for older tests, but you're different error.
And you're also losing the bonuses that you got in the past.
Yes, older bonuses have lost their effect, but older losses also lose their effect. But it gives a little bit more stability to the procedure over time.
Yeah, I understand. Thanks.
Yanis, do you want to ask a question yourself, or do you want me to read out, Yanis?
Oh yeah, sure. Yeah, I can bring my face online. Hello. So, is there any way of accounting for the cost of testing hypotheses? So, for example, in large organizations that do A/B testing, there's a final pool of budgets basically allocated for all these A/B tests. I mean, it might look infinite. You know, we're talking about multi-trillion-dollar organizations, but still, right? They would like to control the budget. So, is there any way to account for this aspect in the allocation of alpha?
It's interesting because I think it's kind of a complement to the kind of stuff I was talking about, right? In my approach, you have to compensate for testing, and what you're asking is in case the testing itself actually costs money. And I think if you can allocate a value to each test, then it's actually should be pretty straightforward to do like a maximal total benefit, combining the cost and the power and the benefit from rejection in each test. I think it's a very interesting setup that can be explored.
Yeah, I agree. I haven't seen any work on it. I think because maybe the actual detail of the final objective function you're trying to optimize seems like there's some thought that has to be put into it. Like, do we want to maximize power and effect size? And the thing is that, like, if you do each experiment a little longer, you have a better chance of detecting smaller effects. But the question is, do you want to detect smaller effects? And now that's a question of when Google or whichever tech company launches a change to billions of users, even small effect sizes can result in large revenue for them. So like now there's so many subtleties. Maybe in the sciences we don't care about very small effect sizes, but maybe in tech they do. So I guess I think that makes the problem interesting, but it also means that's why there hasn't been progress, because there isn't a clear way of how to solve the problem.
May I just mention, it's not exactly related, but maybe it's the way I would formulate your question. It's something we've been working on, is optimal multiple testing. So it's optimizing the total expected number of rejections while controlling measures of false discovery.
Right.
So this is a situation where the cost benefit is well defined by just how many rejections you end up with, and then you can come up with optimal policies for doing the testing.
Thank you.
Thank you.
Well, I really enjoyed this this webinar, but I guess I should call it the end. We already kind of running out of time now. So if no more questions, then I guess thank you everyone for joining, and Aaditya, Aharoni, and Lei Fithian. Hope you get well soon, Lei Fithian.
Thank you very much.
Thank you, Yi, for organizing the session. It was wonderful.
Yeah, and especially I just want to thank you, the supporting staff, Judith, Alfie, and Teresa. Yeah, without them, we can't have this very successful webinar. Thank you all.
Absolutely. Thank you very much.
Right. I think all the slides will be available online in due course. And if you have questions, you can. I hope everyone is welcome to be contacted offline. And thank you all. Stay safe and happy holidays.
Thank you.
Thank you very much. Bye-bye.
Thank you. Bye-bye.